Our next speaker, this fun fact is very fitting for the talk they're about to give. He has taken a 3-day train ride from New York to California and highly recommends it. Everyone, please welcome Gayan.
Afternoon, everybody. My name is Gayan. I'm with the MTA, as the song implies, and today I'll be talking about congestion pricing. So, quick introduction. I'm a data scientist on the MTA's data and analytics team. We are very new. We are founded around 2022, and we've grown from about 5 people to around 25 to 30 if you count interns. And our mission at the MTA is to bring modern data infrastructure and analysis to bear within the MTA. So what does that look like? That means building a modern data stack. That means building our outputs to open data, and then answering some of the MTA's most pressing data-relevant challenges. Now, I am going to talk about congestion pricing, but I'm going to be doing so as a model to explain the value of having a data analytics function in a company like the MTA. Our team, Data and Analytics, effectively lives downstream of operations. A lot of the work we do at the MTA is obviously operations, getting trains and buses and railroad trains to customers, to stations, making sure that's all flowing. That's all operational, and they have their own siloed data systems. But what the data and analytics team does is ingest that information and analyze it, making that information available to leaderships so they in turn can improve operations. This is the virtuous cycle we like to think we fit into. So for today's talk, I'm going to start by defining what is congestion pricing and why did we do it. We're going to talk about how we use our data infrastructure to measure whether it's successful or not. And then last, we're going to talk about why we took this approach, why it's important to build that culture of data science at the MTA and organizations throughout government. So first of all, what is congestion pricing? Now, in a theoretical sense, congestion pricing is a surcharge to reduce the demand on a public good. Specifically, when there is excess demand, we know that it causes what we call negative externalities. For those of you who are economists, this is what's known as a Pigovian tax. Now, to put this into concrete terms, the public good in this case is the use of our city streets, the demand is too much traffic, and the negative externalities are all the downsides that causes. For example, slower speeds for both personal vehicles and buses, pollution, and potentially dangerous street conditions. Now, congestion pricing as a means to deal with traffic has existed before, but not in the United States. It's been done in London and Singapore, for example, in this image here. But until this year, again, it had not been done in the United States. So let's talk about the specific conditions of our congestion pricing. It happens in what we call the Central Business District. This is the area south of and including 60th Street in Manhattan. It does exclude the FDR and West Side Highway for those familiar driving here. Now, the Central Business District Tolling Program, CBDTP, that's our specific iteration of congestion pricing, charges vehicles that enter into this zone. This program has 2 goals. As I mentioned before, it's meant to deal with those negative externalities, it's meant to reduce traffic, but it's also meant to raise funds for transit. Specifically, the money from these tolls goes to our capital program, which is used, for example, to purchase new buses and trains. The tricky thing with this kind of toll system, as opposed to a traditional road toll, is that we're dealing with an area rather than a specific street. And so to identify vehicle entries into the CBD, we need a tolling system around the CBD parameter. And if you've ever driven around Manhattan, you might have seen this. This is that perimeter. This is the set of camera gantries at each of the CBD crossings, 60th Street, each of the tunnels and bridges into Lower Manhattan. Now, these cameras take pictures of vehicles as they drive by, they capture the license plate, and they generate tolls for those individuals. So the key thing that they're tracking is vehicle entries, and that's important because vehicle entries are also how we measure program success. The key thing is that we need to have an accurate and singular count of those entries. What I mean is there can't be debate on how many vehicles are coming in because that's necessary for tolling, but it's also necessary for tracking program outcomes. Everything we expect this program to do lives downstream of reduced entries. That's the improved urban ecosystem we're seeking. Safer streets, faster travel, less congestion. Now, again, the key thing to highlight is that this camera system is both used for tolling, using those images, as well as for measuring the impact of that toll itself. So let's talk about how we get the impact of congestion pricing from that camera system. The source system in this case is handled by a vendor. Specifically in this case, TransCore builds and operates that camera system, and they send us the set of vehicle entries from there to send out those tolls. Now, that is a very operational end of things. I mentioned that flowchart earlier. TransCore does maintain a data warehouse. In this case, they have a Microsoft SQL Server endpoint that we can use, we can access, but the data there is not particularly amenable to analysis. So our goal is to take this detailed data set and make it into a form that analysts at the MTA can readily digest. The MTA Data Lake is our solution for that. The MTA Data Lake is the primary product of the data and analytics team. It's a central repository that contains data from multiple different operational or areas across the MTA. That's HR, ridership, bus speeds, all of this lives in a single place, meaning that it's available to all of the analytics who need it. In terms of the software stack, the data exists physically in Azure Cloud. We use Airflow as an orchestration tool in order to build both the ingest jobs that load it from those source systems, as well as for transforming that data, manipulating it, and making it more usable for analysis. All that happens through scripts that run on a Spark cluster, and all of these various aspects are managed as GitLab repositories, allowing any of the changes we make to our ingests or transformation logic to be version controlled. And key to all of this, we don't want to just store this information. We want to make sure that it's usable for analysts throughout the MTA. We make use of Trino to make sure that querying is fast. And all of our tables are documented in admin.syn, which means all of our columns, all of our tables come with descriptions that users throughout the MTA can source for their information. This is a view of what Airflow looks like from our web app. What you see on the right there is the DAG of each of those ETL tasks used to, again, load data from the camera system. On the left of the screen here is the daily schedule of those ingests. Each of those vertical bars, for those unfamiliar with Airflow, represents a single day of data being processed, and each of those green squares underneath are those individual tasks along the way. So this allows our data engineering team to monitor the data as it comes in, running on that daily ingest, and address it as appropriate, increasing cluster resources or bugging folks at TransCore about late arriving data. So again, the result of this whole pipeline, all this infrastructure that we've done, is vehicle entries. And the goal here is for it to be kind of surprisingly simple. A single fact table that has all of the information we need about entries. The goal here is that with a simple query, this is 6 lines of very simple, obvious SQL, I hope, you can identify the number of vehicle entries each day of the program since program live. And this table includes obviously a lot of other cuts, time of day, vehicle class, the place they actually entered from, and all of this is useful for various data analytics that folks at the MTA use to report on this, and I'll get into a little bit of that in a sec. This, for example, is a plot showing those entries. Now, I'm going to walk through this. X-axis is the date of travel into the CBD. Y-axis is the number of trips that actually entered. You can see the start of tolling, and the gray line there represents our counterfactual baseline of how many entries we'd expect each day had the program not happened. And the kind of key thing here is that there is a 11 to 13% reduction beyond that counterfactual. One thing you might notice is that we expect generally traffic into the CBD to be fairly variable throughout the year, and one thing that we've noticed is since tolling, it's become a lot more flat. This is because a lot of the reduction we have is from what we call discretionary travel, people who could choose to use a car but are now potentially choosing to take transit in, as do again 90% of visitors to the CBD. In terms of concrete terms, this means about 70,000 fewer vehicles coming in each day. Now, there are a lot of fun ways to visualize 70,000 vehicles a day. This is my personal favorite, which is if you take each of those vehicles and you line them up bumper to bumper, that's 70,000 vehicles, that's enough to get you from this office to the particular reason, let's be clear. It's again about 240 miles of vehicles. So why did we take this approach? Why does this data analytics team exist at the MTA? Now, in the specific case, it's because we were legally required to do so. The same legislation that directs the MTA to have congestion pricing also requires that we produce a report 1 year after system live in order to summarize the program's effect on things like, again, vehicle entries, traffic, and pollution. Now, as part of that process, our team works closely with the team that is working on that report right now, I believe. And what's key is that they have access to that same data lake, all those information about vehicle entries, but also transit ridership and pollution. All of that data is also ingested on the lake for them to use. This is replacing a system where folks are simply sending around Excel sheets in emails as a way to aggregate these reports, allowing them to take a lot more time and detail into the kind of analyses that prove out the effects of congestion pricing. That said, this is, again, the first in a nation tolling program, and the MTA was unable to just say, wait a whole year for results from this program. Now, the program went live, as I mentioned, January 5th, 2025. And when did people want results about it? January 6th, 2025. Now, of course, because we had set up this infrastructure, we were able to load some of that data on that day, but we didn't want to publicize 24 hours of results to the public yet. But again, because we had this infrastructure, 1 week after program live, we were able to make a public briefing. For those of you who read the New York Times, this was an article in the Times on the 6th, I believe, and it has these numbers categorizing the entries to the CBD as well as the reduction, that same reduction I presented earlier, and these numbers came directly from that same airflow pipeline I shared earlier. We also made sure that we don't treat this as data that we only have control over. We wanted to be open about this data, so we sent it to New York State Open Data. And we did this 3 weeks into the program, which by all means seems to be a record for a public program, and certainly a public program of this scale. For those folks who didn't have the same expertise that this room has, we also have a metrics page with a convenient streamlit visualization showing those entries as well as the relevant information. I want to highlight that what we have here is also the most detailed view we've ever had into vehicular travel into Manhattan. There's obviously all sorts of road studies, but most of these are done with manual counts or fairly outdated camera systems. When your camera system is also your subject of tolling, you make sure you get your counts right. And I want to stress that this is now coming in every day, released on open data, specifically on a weekly cadence up to the previous week. And it's available for all sorts of traffic analytics, which I'll show a small sample of in a little bit. So speaking of, let's use vehicle entries as a foundation for analytics. Now, all the sort of work that we did makes this readily available on our data lake, and here's the kind of things we can do with it. We can forecast future entries. Now this is useful because it's good to know how many folks are coming in for toll collection purposes. Most importantly, knowing how much money you're going to expect to pull in, but also things like, as an example, there was the New Jersey transit strike, and we were able to get a sense of how much more traffic we'd expect as a result of it. We can also compare the number of entries to local vehicle traffic speeds, which allows proving out some results that had previously really only been done, again, either theoretically or on very small samples. Now, this is work that we do closely with New York City Department of Transportation. You can see an example here. X-axis here is that same vehicle entries. Y-axis is the average speed in miles per hour in the zone. And each of those dots represents a single day's average. Now, the sort of obvious trend that you might expect from seeing this is that the fewer people drive into the CBD, the faster the vehicle speeds are. And you see that there's like a slow curve. And this actually proves out something that exists in a lot of traffic studies. One other thing I'd point out is that if you go much further past this, there's a much more precipitous drop-off. And one of the difficult things about showing data that's only post-program, you don't have a sense of exactly what it would look like in a world without it in this case, but we do understand that this small 11 to 13% reduction is enough to effectively prevent us from reaching a threshold where you get much worse gridlock. One other thing I'd point out here is we, as I mentioned, have all sorts of other data sources on the data lake, one of them being bus GPS speeds. So this is a map of the average speed at various points along a route, specifically in this case, the northbound SIM24 bus from Staten Island into Manhattan. This is one of our express buses that actually picks up mostly folks in Staten Island, travels through a bit of New Jersey, takes the Lincoln Tunnel into Manhattan, and then drops some people off. And what you can see here, blue line is post-congestion pricing launch. Gray line is the January 2024 baseline. I will say this data is just from January 2025. The kind of key thing here is that for most of the route, the speeds between the 2 years are fairly comparable, but there's this very specific increase right at the end between miles 25 and 27. That corresponds to the Lincoln Tunnel, one of the entries into the CBD. Therefore, this is demonstrating that removing that additional traffic results in a fairly significant increase in speed over that stretch for that bus, which again serves, I believe, 70,000, 80,000 riders each year, and is obviously just one of our many buses. So, in conclusion, congestion pricing was a first-in-the-nation program to reprioritize how New Yorkers use their streets, supporting the vast majority of New Yorkers who take transit into the city. Two, the MTA data and analytics team defined our company's ability to both understand the data, but also communicate about congestion pricing. Again, putting out and controlling the narrative within a week of program launch. And then finally, this is part of an overarching mission on our company to bring visibility to all aspects of our operations, be that internal work to improve how leadership understands the various levers they have to control, as well as releasing that data to open data and making sure that the public can all contribute to improvement of our system. I want to highlight the other folks on our team who've made this effort possible, and I want to thank the Lander Analytics Conference to hosting us.